So far, we've been concerned with how fluids behave in the static case, when there is no fluid flow. We can, however, also investigate the principles that govern the flow of fluid. We can distinguish between two main types of flow. The first is laminar flow, and this type of flow is characterized by a smooth streamlined flow such that neighboring layers of the fluid slide over each other smoothly. The second type of flow, which occurs above certain speeds, is called turbulent flow. Turbulent flow is chaotic and unstable, with a lot of irregularities, such as eddy currents and swirls. We're now going to see how we can apply the principle of conservation of mass to fluids in motion. To do this, we'll consider a section of a pipe through which fluid flows continuously, and at this section, the pipe changes diameter. This section of pipe under observation is called a control volume, since it remains constant in volume as fluid passes through it. If we observe this section of the pipe for a very small amount of time, say delta t, we'll see that within this period of time, some amount of fluid flows into the pipe and some amount flows out of it. Applying the principle of conservation of mass, we can deduce that all the mass of fluid that goes into our control volume within time delta t either remains within the control volume or flows out through the other end. What this means is that if we somehow had a way to measure the total mass of fluid that entered our control volume within time delta t, it would be equal to the change in mass of fluid within our control volume plus the total mass that flowed out of our control volume. And to explain how this would really work, if 5 kilograms of fluid flowed into our control volume, and in the same amount of time 3 kilograms flowed out, it would mean that the mass of fluid in the control volume would have increased by 2 kilograms. On the other hand, if it was 3 kilograms of fluid that flowed in and 5 kilograms flowed out, then the mass of fluid within our control volume would have increased by 2 kilograms in that time frame. So back to this. If we divide our equation through by the time delta t, on the left hand side we have, in terms of mass, the rate at which fluid flows into our control volume with respect to time. This is called the mass flow rate. And on the right hand side we have the rate of change of mass of fluid within the control volume with respect to time, plus the mass flow rate out of the control volume. This equation is called the continuity equation, and we can write it in many different ways. We can write the mass flow rate of a fluid in or out of a pipe of known cross-sectional area in terms of the fluid's density and velocity. Let's say some mass of fluid flows into a pipe within time delta t. This mass of fluid is equal to its density multiplied by the volume it takes up in the pipe. And this volume is equal to the cross-sectional area of the pipe multiplied by the length of the pipe through which the fluid extends. So the mass of fluid delta m equals the density multiplied by the area multiplied by the length through which the fluid extends. The mass flow rate, which is delta m divided by delta t, is therefore equal to rho A delta L divided by delta t. By definition, delta L divided by delta t, which is the rate at which the fluid extends further into the pipe, is the velocity of the fluid at the pipe entrance, v. So our mass flow rate equals rho AV. And this is the relationship between the mass flow rate of a fluid and its density and volume. Applying this to our continuity equation, if we call the inlet into our control volume point 1 and the outlet point 2, we can write rho 1 A1 V1, which is the mass flow rate at point 1, equals delta m divided by delta t, which is the rate of change of the mass of fluid within our control volume, plus rho 2 A2 V2, which is the mass flow rate at point 2. If the fluid is incompressible, then the density remains constant throughout and rho 1 equals rho 2. Also, constant density means the only way for the mass within our control volume to change is to change the volume. But that can't happen, since the control volume is constant in volume. This means, for an incompressible fluid, the mass within the control volume doesn't change. So the rate of change of mass, delta m divided by delta t, equals 0. Our equation is therefore reduced to rho A1 V1 equals rho A2 V2, and we can cancel out the densities. So this gives us A1 V1 equals A2 V2. This equation shows the variation in fluid velocity from one point to another within a pipe of non-uniform cross-sectional area for incompressible fluids. Bernoulli's principle is an important concept in fluid dynamics that relates fluid pressure, velocity, and height. Bernoulli's principle states that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. Bernoulli's equation expresses Bernoulli's principle mathematically, and we can derive Bernoulli's equation for a steady-state incompressible flow using the principle of conservation of mechanical energy. A steady flow is one in which the conditions such as velocity and pressure may differ from point to point, but do not change with time. To derive Bernoulli's equation, we are going to consider the steady incompressible flow of a fluid through a pipe which changes diameter and height. Since the fluid is incompressible, we know its velocity changes when it goes from the wider section of the pipe to the narrow section by applying A1V1 equals A2V2, which we obtained from our continuity equation for incompressible fluids. The potential energy of the fluid also changes since there is a change in the height of the pipe. Bernoulli's principle tells us that along with this change in velocity and potential energy, there will also be a change in pressure between the wide and narrow portions of the pipe or tube. We'll call the pressure in the wide portion P1 and the pressure in the narrow portion P2. And we're going to use the work energy principle to analyze a parcel of fluid which flows through this change in height and diameter. The parcel of fluid experiences static pressure at both ends due to the surrounding fluid. These pressures, multiplied by their respective cross-sectional areas, constitute forces. So as the parcel of fluid moves towards the right, the pressure P1 pushes it through a distance delta L1, and simultaneously the pressure P2 pushes against it in a direction opposite its direction of motion through a distance delta L2. The work done on this parcel of fluid in the direction of its motion is therefore F1 delta L1 minus F2 delta L2. F2 is negative because it opposes the fluid's displacement. F1 and F2 are results of the pressures, so F1 equals P1A1 and F2 equals P2A2. So we can write our work done W as P1A1 delta L1 minus P2A2 delta L2. The volume of fluid which extends through delta L1 in the wide portion of the pipe is the same volume of fluid which extends through delta L2 in the narrow portion. So A1 delta L1 and A2 delta L2 are both equal to a particular volume V. We can therefore write the work done as V into P1 minus P2. Next, we'll consider the change in potential energy of the fluid. To make this easier to understand, I'll break off the pipe into sections A, B, and C. In the initial case, the fluid only takes up sections A and B. The total potential energy of the fluid is equal to the potential energy of the fluid within A plus the potential energy of the fluid within B. Since the fluid within A remains at a constant height throughout, its potential energy can be calculated. And the potential energy of the fluid within A is equal to its mass multiplied by the acceleration due to gravity multiplied by h1, which is its height above our reference level. This mass can be written as density multiplied by its volume. So we have the potential energy of the fluid within A equals rho v gh1. It would be difficult to calculate the potential energy of the fluid within section B because the height and cross-sectional area changes throughout. So we're just going to leave it as it is. And therefore the entire potential energy of our fluid in the initial state equals rho v gh1 plus the potential energy of the fluid within B. At the final state, the fluid only occupies sections B and C. So the potential energy equals the potential energy within B plus the potential energy within C. The potential energy of the fluid within C can be written as rho VGH2. So the total potential energy of the fluid in our final state equals the potential energy of the fluid within B plus rho VGH2. We can write the change in potential energy, and with this subtraction we can see that the potential energy of the fluid within B in both cases are equal and cancel out. So we're left with rho Vg into H2 minus H1 as our difference in potential energy. Lastly, we'll determine the change in kinetic energy of our fluid. Again, using our sections A, B, and C. Initially, the fluid occupies sections A and B, and its total kinetic energy would be the kinetic energy of the fluid within section A, plus the kinetic energy of the fluid within section B. The kinetic energy of the fluid within section A is equal to half of its mass multiplied by its velocity, which gives half ma v1 squared. We can again write its mass as the product of its density and volume. So the kinetic energy of the fluid within A is equal to half rho v for volume times v1 squared, where v1 is its velocity. The diameter changes throughout section B, so fluid velocity varies within it, and we can't easily calculate its kinetic energy. So the kinetic energy in the initial phase is just going to be half rho v times v1 squared plus the kinetic energy of the fluid within B. Now in the final state, our fluid occupies only sections B and C. So its total kinetic energy would be the kinetic energy within B plus the kinetic energy within C. And the kinetic energy within C equals 1 over 2 rho v times v2 squared. So the total kinetic energy in the final state equals the kinetic energy of the fluid within section B plus 1 over 2 rho v times v2 squared. Since our flow is steady, the velocity at any particular point, or the average velocity within a particular region, doesn't change over time. So the kinetic energy of the fluid within section B in the initial and final state doesn't change. The change in kinetic energy is therefore equal to 1 over 2 rho v into v2 squared minus v1 squared, where v2 and v1 are the final and initial velocities respectively. The work energy principle tells us that the total work done on a system is the sum of the change in its potential and kinetic energies. So V into P1 minus P2 equals rho Vg into H2 minus H1 plus 1 over 2 rho V into V2 squared minus V1 squared. We can cancel out the volume on both sides. So we're left with P1 minus P2 equals rho G into H2 minus H1 plus 1 over 2 rho V2 squared minus V1 squared. This equation shows us the relationship between a change in height, velocity, and internal pressure of the fluid. We can rewrite this as P1 plus half rho V1 squared plus rho GH1 equals P2 plus half rho V2 squared plus rho GH2. This is Bernoulli's equation, and since points 1 and 2 can apply to any 2 points along the pipe, it can also be written as P plus 1 over 2 rho V squared plus rho GH is constant at every point in the fluid.